Hi, the project is on efficient feature extraction algorithm on FPGA devices. In computer vision systems, feature extraction and object detection are critical applications as they play important role in real-time systems. The feature extraction kernel started gaining diversified applications in day-to-day life. Real-time image search engine, virtual reality have all started seeing their larger use of feature extraction algorithms. The need for faster and efficient feature extraction algorithm is driving the research community to research and publish the work related to feature extractions. The 2D and 3D modeling applications is seeing their applications outside of robotics in the latest. The task that feature extraction algorithms are trying to achieve is to achieve reliable object detection from a given set of images of the objects. Although there are several algorithms to perform the object matching, there is no single efficient algorithm which is widely accepted. For a given feature extraction algorithm, several performance parameters must be taken into consideration and its design space for a given system should be explored to attain the optimal performance. The design parameters affecting the performance of the kernels are affine transformation, scale, orientation, illumination, blurring. The change in the parameter mentioned before results in loss of features affecting the object matching algorithm, as the features of the object play a major role in extracting the information. There have been several studies performed on feature extraction algorithm comparing their performance in terms of execution time, precision, cost, and power consumption. In this work, I have explored the design parameters and performed a comparative studies between different feature extraction algorithms. The algorithms under investigation in this paper are SIFT, SURF, FAST, ORB, BRISC, and FREAK. These algorithms are then later evaluated on OpenCV framework and is finally developed, and its performance is evaluated on Zinc 7020 FPGA. SIFT. SIFT is a feature extraction algorithm and it has two parts, one detector and descriptor. The detector part extracts the corners or edges, and then later the second stage, which is descriptor, does a description part which gives information to the feature that has been extracted. SIFT or scale invariant feature transform is composed of four critical stages, namely scale space detection, key point localization, key point descriptor, and orientation assignment. In case of scale space detection, the DOG or the difference of Gaussian is used to find the potential points that do not vary in scale or orientation. In order to boost the computation speed, DOG is preferred to the Gaussian. Here, the convolution operator is the variable scale Gaussian is g of x, y, r for the image x, y. And the difference of Gaussian to the scale of k is d of x, y, r. The points of lower contrast are eliminated edge response are rejected in the key point localization step. The principal curvature is calculated by a Hessian matrix, and the key points which have higher ratio are then between the curvatures are eliminated. Based on the gradient orientation of points in a region surrounding the key point, histogram of orientation is plotted to obtain the orientation assignment, as shown in the image. Throughout the experimentation yielded the best results for a 4x4 array of histograms, each with 8 bins for orientation, and hence the descriptor of SIFT has 4x4x8, which is 128 dimensions, as shown in the image. The OpenCV benchmark of SIFT shows that the execution time of SIFT is as high as 1 second. So the extractor takes a huge amount of time in computation and shows that it is compute intensive detector. The descriptor part depends upon the number of features that has been extracted by the detector. So the descriptive time increases with the number of detector features as shown in the graph. Match time also increases as expected with more features to match. Surf. To make sure the features detection steps are fast enough, speed up robust feature detector or SURF was designed. Without sacrificing on quality of detected points, SURF enhanced the speed of SIF's detection process. Unlike the PCA SIFT, SIFT and SURF algorithms' way of detecting features varies slightly. SIFT uses Gaussian to filter with growing sigma values and performs the difference to build image pyramids, while SURF for higher level doesn't downsample yet creates a stacking resulting in images of space resolution. During the key point matching step, the key point with minimum Euclidean distance is identified as the closest neighbor using the matrix fast Asian matrix shown in the image. Again, the surf consists of two stages. One is detector and descriptor. Detector part imparts some scale invariance to the images, making it robust to rotation and scale change. The key computation part involved in this is the calculation of Haar wavelet. It can be seen that the execution time of SIFT is much higher than that of the SURF. The SIFT takes about 1 second to compute 3000 features. However, SURF takes only about 100 milliseconds, which is 10 times lesser than that of the SIFT. As opposed to the real valued computation being done in SIFT and SURF, there has been another category where the computation is performed at the bit level, and these are called binary detectors and descriptors. The key properties of binary detectors and descriptors is that it is composed of binary string and does only simple brightness comparisons, which is less compute intensive compared to the SIFT and SURF algorithm. This makes binary detector descriptors well suited for real-time, low-power systems. The general property of binary descriptor is that it uses Hamming distance instead of Euclidean distance for matching. Hamming distance is nothing but performing an XOR of two bit vector and calculating the resultant value. Or commonly known as oriented fast and rotated brief, where fast is used for detector and brief is used for descriptor part. Fast is a corner detector, also known as features from accelerated segment test. Fast detects corner points, which are widely used feature point extraction and computer vision job tracking and mapping algorithm. This algorithm was developed by Tom Drumpton and published in 2006. Computational efficiency is a star aspect of this algorithm, and being true to it, it is the fastest among other popular methods like Harris, Susan, and other difference of Gaussians. Applying machine learning algorithms will steer up the performance utilizing less time and computational resources. Owing to its enhanced performance, FAST is perfect for processing real-time video applications. In order to determine if a point is a corner, FAST uses a 16 pixel Bresman circle of radius 3. Every pixel of the circle is clockwisely labeled from integers 1 to 16 as shown in the image. P is a corner. If there are 12 continuous pixels, which is brighter in intensity than the center pixel, which is the pixel under investigation. When any of these conditions is satisfied, pixel P is determined as a corner. Performance trade-off between the number of features extracted and computational intensity of kernel is made through changing the threshold value. An optimal point is achieved through experimental analysis and observation was made. The descriptive part is brief, which is used to extract the information and provide a bit vector to the feature that has been extracted. Oriented fast does n comparisons on the Bresman circle. Feature detection process is embarrassingly parallel and can suit FPGA architectures. The key computation part involved is calculation of intensity centroid, which is the orientation part of the fast. Brief does a 52-bit length descriptor generated by pairwise intensity comparison in every feature window. Brisk and freak is a variant of brief, where the sampling pattern is varied. It is very significant to observe the use of brisk detector in combination with other key point descriptors like ORB as mentioned earlier. The work of Matt inspired the methodology to detect a region of interest in an image with a focus on efficiency of computation in scale space key detection. Agast is more likely an extended form of the fast for an accelerated performance and efficient extraction of features. The maxima is also searched in the scale space in addition to the image plane, and the salience is measured by the fast score to achieve zero variance, which is very critical for precision of key points. In spite of having a discrete axis at coarser intervals instead of alternative high performance detectors, brisk detectors estimate a true scale in continuous scale space for every key point. The layers in the scale space pyramid in brisk work have n number of octaves called Ci and n number of intra-octaves. These octaves are a result of progressive half sampling of the actual image. In freak detector, pairs of pixel intensities can be compared with many possible sampling grids. Like DAISY, Brisk deploys a circular structure of equally spaced points on concentric circles as shown in the image. The sampling grid of Freak is inspired from the retinal pattern. The grid of Freak is circular in shape similar to Brisk, however, at the center of the points are denser as shown in the image. Sampling window is smoothened using filter to make it less noise sensitive. ORB and Brief both use random pixel points in the window, and also some same kernel is used for all points in the window patch. However, different size kernels are used to every sample to match the retina mode of Brisk. But in Brisk, change in size is exponential and receptive fields which are overlapping differentiates itself from the others. We have experimentally observed that the performance increases with Gaussian kernel size as it plays a major role in performance. The experimental analysis shows that the execution time of ORB is much less compared to SIFT and SURF. The execution time of ORB is as close to 14 milliseconds as opposed to SIFT and SURF, which takes in the order of 100 and 1000 milliseconds. On comparison between ORB and Brisk, the execution time is fairly close. However, the variation of execution time in Brisk is exponential. The evaluation of Freak shows that the execution time is higher than that of uh, ORB and Brisk, thereby making Brisk the efficient algorithm when compared to ORB and Freak. The ORB can be employed in combination with Brisk to achieve higher performance, and it can be noticed that the execution time is drastically reduced when compared to ORB. The execution time of ORB is 14 milliseconds. However, the execution time of ORB Brisk for 3000 feature points is just 7 milliseconds, which is half of the ORB combination. So, in summary, we can see that uh, ORB, BRISC, and FREEZE have different detector and descriptor computation algorithms, and in terms of execution time, Freak takes the least amount of time and memory footprint. In addition to the execution time, these extraction algorithms are also evaluated in terms of precision. So when the image is affected by scale, intensity and rotations, the precision of image matching would drastically reduce. The amount of the performance of these kernels can be evaluated in terms of precision that to indicate that the confidence at which the object can be matched in spite of the intensity, rotation and scale changes is measured. The precision is the ratio of number of correct matches to the total number of positive matches. Rotation invariance. In any real-time vision systems, the camera input might be subjected to environmental influences causing a deviation from the original image. The deviation caused by external environmental influences makes it difficult for image matching kernel to match the real-time images with features from the database. With rotation of angle of 0, 90 degree, 180, 240 and 360, we could see that the matching confidence is has close to 1. It indicates that all the algorithms performs well without much change in the rotation angle. However, for the other angles, it could be noticed that the SIFT and SURF outperforms all the other algorithms, as the SIFT and SURF is robust. Scale invariance. The deviation caused by the external influence makes it difficult for image matching kernel to match the real-time image with the features from the database. Scale change, the change due to zoom in and out, results in altered scene affecting the performance of image matching. Our study involves that study of performance variation with varying zoom factor, which is the x-axis scale. It can be seen that at a zoom factor of 1, that is without any change in scale, all the algorithms perform an accurate object matching. However, at a zoom factor of zero point 0.5, which is scaled down, a SIFT and SURF performs robustly well, as it is scale invariant. However, orb and its variance does not perform well, and the confidence in matching reduces below 50%. This indicates that we could perform image matching by scaling down to 50% at most. This increases the execution time. This decreases the execution time and increases the performance. Intensity invariance. In external lighting conditions affect the performance of feature extraction, as intensity of pixel plays a major role in orb kernel operation. The experimental result shows that at brighter conditions, SIFT and SURF is able to extract all features, however ORB does not. However, in darker condition, SIFT and SURF does not perform well, as it loses all the feature points. Concluding that ORB outperforms SIFT and SURF in majority of the cases, and it can suit real-time performance. I have further ventured into the hardware architecture of FAST and its implementation on FPGA. So the FPGA module consists of different processing modules known as threshold module, contiguity module, corner square module, and non-maximum suppression, each of which is to detect a corner and check for the condition to analyze if it is a feature point or not. So the latency for performing such evaluation is as close to buffering 7 rows of pixels of an image. So this is a convolution type approach and it suits low latency approach for any FPGA applications. So the fast corner detector has BRAM address generator to buffer in all the values into the BRAM and extract the required pixels, that is the 16 pixels in the circle of Breastman. These 16 pixels are then sent to threshold module which performs a comparison values and extracts the necessary information. The information is then sent to cornerscope module which then decides if the extracted value is a corner or not. The pipeline induces a latency of 7 clock cycles. Based on the fast architecture, I further evaluated the functionality of the architecture by simulating it in HDL simulation environment. The input image is a bridge which is sent into the FPGA architecture, and at the output all the corners are highlighted in a static image. We could see that hardware fast detector extracts all the necessary modules, however, and it is compared with the OpenCV for comparison purposes. The hardware architecture is then evaluated on latest ECP3 device and the performance is obtained. It can be noticed that the resources is close to 5% for corner detector alone and the dynamic power consumption is as close to 350 milliwatt, and thus it suits low latency and low power approach. Thank you.